In this video, we will practice more of the more problems involving the comparison test. And you can open the definition of the comparison tests either in your notes or in your book. Have them in front of you. Okay, I'm not going to write them here. I'm just going to do problems. So let's start right away with the first problem. Of course, the question is determine if this series is convergent or divergent. One easy problem for the warm-up. N times square root of n squared minus 1. Okay. So right away, when you're doing the comparison test, always have in mind in your toolbox, right, what are we going to operate with? So have in mind these two series, that's the P series and the geometric series. So have in mind the sum of 1 over n to the power of P, that is convergent when P is greater than 1, and the geometric series A times R to power n, that is convergent when the absolute value of the ratio is less than 1. Okay, so these are the one that we're going to use them. Okay, so here which one we can use, right? Where is our go-to series? Well, look at this is my series AN, right? So take the series BN to be defined as 1 over the highest exponent in the denominator of AN. So here I have n times square root of n squared. N is a positive integer, so square root of n squared is just going to be n. N times n is n squared. Okay, and obviously we are talking about the P series. And then tell me why, because P is equal to 2 greater than 1. Okay, and now the only thing that's left is for you to determine what test are you going to use, either the comparison test or the limit comparison test. So the limit comparison test just asks you what is the limit of the ratio of AN over BN. So the question is, what is the limit of 1 over n square root of n squared minus 1 over 1 over n squared, that's your Bn, right? As n goes to infinity, and this is equal to the limit of n squared over n square root of n squared minus 1 as n goes to infinity. Okay, so I have this element times this divided by this times this. Okay, and this element, factor from here n squared over n times n square root of 1 minus 1 over n squared. As n goes to infinity, we obtain 1, because 1 over n squared goes to 0, so this limit is equal to 1, which is greater than 0. And then you can see by the limit comparison test, both of this, as if the limit of an over bn is a constant greater than 1, then both series behave the same. Because sum of bn is convergent, then sum of an also has to be convergent. Okay? So let's do second example. The question is always the same. Determine whether the series is convergent or divergent to the power n over n squared 2 to the power of n. Okay, so you might we can solve this in two different ways. Okay, one of them is to compare it to the highest to the highest exponent, the numerator and denominator, and that's 2 to the power n over 2 to the power n. So if they cancel, then I get only 1. So it doesn't say anything. But then can I compare it 2 to the power of n over n squared 2 to the power of n. Okay, so what I'm taking, the highest exponent of the numerator divided by the whole denominator. But now when I simplify this, I get sum of 1 over n squared, which is a convergent p-series. Okay, with p greater than 1. Okay, now again, I can take the limit comparison test. So I have to check what happens with this ratio. That's the limit of n plus 2 to the power n over n squared 2 to the power of n over 2 to the power of n over n squared 2 to the power of n. Now we can cancel these two terms, and that is the limit of n plus 2 to the power of n over 2 to the power of n, of course, as n goes to infinity. And now, what is the highest exponent? We said that the exponential sequence goes much faster than the linear sequence right here, so I can just right away, I know that this limit is going to be 1. If you are not as comfortable with that, then just factor the leading term in the numerator, that's 2 to the power of n over 2 to the power of n. Now we cancel these two terms. As n goes to infinity, as I said, the order of growth is much bigger with 2 to the power of n, which means for this particular ratio, the denominator pulls down and the whole ratio goes to 0. So this ratio is 1 greater than 0. So by the limit comparison test, here you have proved that the limit comparison test gives us a conclusion. The conclusion is that both of the series, sum of an and sum of bn, they behave the same. Since sum of bn is convergent, by the limit comparison test, we have shown that sum of an, which is n plus 2 to the power n over n squared 2 to the power n, is convergent. Okay. Another way to do this, and I'm going to leave this for you, what you can do. So maybe for some of you it would be natural just to start this problem by splitting this series into this expression here into two expressions, n squared 2 to the power n plus sum of 2 to the power n over n squared 2 to the power n, and then treat these two different sequences. So this is going to be equal to sum of 1 over n 2 to the power n, because I cancel these two, okay, plus sum of 1 over n squared, because here I cancel these two, okay. So the first sum, so I'm just gonna go, I start the same problem just by splitting these two terms, right? This is a sum, so I can express this two different fractions here. So the first sum, so this one, 1 over n to the power n, is convergent by the comparison test. Why? Because 1 over 2 to the power of n is a convergent geometric series, and 1 over n 2 to the power n is less than 1 over 2 to the power n. Okay, so the comparison test is satisfied. And the second series the second summand is a convergent p-series. So there you go. You have two different ways how to do this particular problem. Okay, and now let's move on to the third problem. Sum as n goes from 1 to infinity ln of n over n plus 1. Okay, so although we said that we're just going to do the comparison test, it is good from time to time to throw you off a little bit, and this is what happens in the book if you do the questions, just to build up your intuition, right? It doesn't mean that whenever you see a series, you don't box yourself of thinking, I have to use this test or that test. The best thing always to do is just to try and do the test for divergence. So for each problem, you always do the test for divergence first, mentally. So what happens when n goes to infinity? This ratio goes to 1. Okay, so ln of 1 is 0. So the limit of an goes to 0. That means the test for divergence is inconclusive. Okay, next one, we have done this problem. Properties of logarithmic function, ln of a over b is ln of a minus ln of b. And now I'm going to treat this as a telescoping series. And the telescoping series said what? Find the limit of Sn and check whether it converges or diverges. Why? Because by definition, sum of an is equal to the limit of Sn as n goes to infinity. Okay, this is very important. Okay, it's gonna come back over and over. So this is the definition of infinite sums, right? This is the nth partial sum. So what is the nth partial sum? When n is 1, I get ln of 1 minus ln of 2, right? 1 plus 1 is 2. Plus, now ln becomes 2. ln of 2 minus ln of, when n is 2, this is 3. Plus ln, now n becomes 3. ln of 3 minus, ln of 4 plus, and so on and so on. And then we can do when n is n minus 1, right? So ln of n minus 1 plus ln of n minus 1 plus 1 is just ln of n minus, so the nth term is ln of n. This is minus, I'm sorry again, so this is plus ln of n minus ln of n plus 1. Then you can see that this is a telescoping series. All of these terms cancel, right? ln of 4 is going to cancel with the next one. ln of n minus 1 is going to cancel with the one prior to that one. Negative ln of n and ln of n. So we are left with Sn being equal to ln of 1 minus ln of n plus 1, which is equal to negative ln of n plus 1. Why? Because ln of 1 is 0. Well, then by this definition, all we have to do is find the limit of the nth partial sum and that's equal to negative infinity, which implies that sum of an is divergent. right? So again, the idea of this problem to be thrown in the mix of these problems that can be solved with the comparison test is that you always expect something like this. Always, first of all, check the test for divergence. If that doesn't give you any conclusion, don't get fixed on the idea that you have to use this or that particular test. Okay, so let's move on now. Problem number 4. Sum of 2 to the power of n plus 3 to the power of n over 3 to the power of n plus 4 to the power of n goes from 1 to infinity. Okay, again, you can split this into two different series, or compare it to the highest term in the numerator and the highest term in the denominator. That's 3 to the power of n over 4 to the power of n, which is the geometric series, convergent geometric series. With r being 3 over 4 less than 1. And now do the limit comparison test. The limit as n goes to infinity of an over bn is equal to the limit of 2 to the power n plus 3 to the power n over 3 to the power n plus 4 to the power n over 3 to the power n over 4 to the power n. Multiply this term times the numerator. That gives you 8 to the power n plus 12 to the power n over this term times this term, 9 to the power n plus 12 to the power n. Now how are we going to solve this limit? Factor the leading term. So we have 8 over 12 to the power of n plus 1 over 12 to the power n and 9 over 12 to the power n plus 1. And now these terms are going to cancel. These terms are going to go to 0, so this limit is 1, which is greater to 0. And by the limit comparison test, the sum of an converges. By the limit comparison test. Here I just want to remind you, if anybody forgot, that if you have a ratio to power n, the sequence as n goes to infinity, this limit goes to 0 as long as the ratio is less than 1, and 8 over 12 is less than 1, and 9 over 12 is less than 1. That's why that sequence goes to 0. Okay, so let us do problem number 5. Sum of 1 over n factorial as n goes from 1 to infinity. And of course we will see another way how to solve this series next week. Okay, but for now, can I solve it? Well, of course I can solve it. What do we know? We know that the limit 2 to the power of n over n factorial goes to 0 as n goes to infinity, right? We know that because n factorial, the order of growth of n factorial is bigger than 2 to the power of n, so this pulls to infinity much faster, so that brings this ratio to power 0. Okay, so why do I do this? How am I going to get from here? How am I going to get to here? So I want to find the limit of an over bn to end up being limit of 2 to the power n over n factorial. Well, how that is going to happen? If I take bn is equal to 1 over 2 to the power of n, which is geometric convergent series. And then if bn is 1 over 2 to the power of n, this is the limit of 1 over n factorial over 1 over 2 to the power of n. And now this term times this term divided by n factorial times 1 gives us exactly what we want. And this is 0, right? This limit is 0. And we said that as long as if sum of bn is convergent and the limit of an over bn is equal to 0, then sum of an is also convergent. So this situation, when the limit is 0, works only when our series bn is convergent, and that's what we have here. So I can use this version of the limit comparison test. Okay, let's look at the next problem, problem 6. Sum of n minus 1 factorial over n plus 2 factorial, n goes from 1 to infinity. This problem here asks us to simplify this. Whenever factorials are involved, check whether you can simplify this a little bit. And this always express the bigger factorial in terms of the smaller factorial. So n minus 1 is less than n plus 2, so I'm going to keep the smaller factorial as it is. And then the bigger factorial is n plus 2 times 1 less, which is n minus 1, plus 1. 1 less than n plus 2 is n plus 1. 1 less than n plus 1 is n. 1 less than n is n minus 1. And here I stop. Why? Well, because now I can cancel. Now I can cancel the n minus 1 factorial, and the new expression for the same series is n plus 1, n plus 2. And goes from 1 to infinity. Okay, so let us take sum of 1 over n to the power of 3, which is a convergent p-series with p greater than 1, p is 3 greater than 1. And then look at this. N times n plus 1 times n plus 2 is greater than n times n times n, right? N is equal to n plus 1 is greater than n plus 2 is greater than n, so n times n plus 1 times n plus 2 is greater than n cubed. N times n can be written as n cubed, right? But now if I take the reciprocal, I have 1 over n times n plus 1 times n plus 2 is less than 1 over n cubed. This was my bn, this was my an. So we conclude by the comparison test sum of n minus 1 factorial over n plus 1 plus 2 factorial, which was the sum of an, is also convergent. Okay, of course, if you do the limit comparison test, then the limit of an over bn would have been 1, so the limit comparison test also works. Okay, so let's do problem 7. Sum of a negative 1 to power n, e to the power of 2x over e to the power of 2x plus 1, and goes from 1 to infinity. The first thing that you have to notice is that neither the integral test nor the comparison test can be applied to this series. Why? Because this is not a series with positive terms only. Every second term is negative. So what tools do we have so far? So far I have the telescoping series, right? That is different than limit comparison test and and the integral test, and I have the test for divergence. So let's check whether this limit is 0. So how much is the limit of an, right, as n goes to infinity? Well, the limit of absolute value of an, taking away the alternating part, is equal to the limit of e to the power 2x over e to the power of 2x plus 1, and this is 1. Which implies, this is only the absolute value, which implies that if you put this alternating part here, which means that the limit of an does not exist, because as we're going towards infinity, the absolute value of an is 1, so plus the times the alternating part is going to be positive 1, negative 1, positive 1, negative 1, so that means that the limit does not exist, which finally implies that by the test for divergence, an is divergent. So again, always be ready to test that, to use that test for divergence. Okay, the next problem, arcsecant of n over n to the power 1 over 3. So I have the arcsecant function here, and what do I know about the arcsecant function? I know that the arcsecant is bounded above by 3 pi over 2. Right, so this is the graph. The graph of arcsecant, right? But then also you can easily take the upper bound 3 pi over 2, so this is pi over 2, this is pi, this is 3 pi over 2. If you want to be more precise, you can say even pi over 2. And why do I say this? Because n is only positive, right? So I can just concentrate on this part of the graph. So it's bounded by pi over 2. And as a matter of fact, it's bounded by any constant greater than pi over 2. Okay? So let my Bn sequence be whatever, 2 pi over n to the power 1 over 3. Which is 2 pi times 1 over n to the power 1 over 3 as a sum, which is a convergent p-series, where p is 1.3 and that's greater than 1. Okay? But then, since arcsecant of n is less than 2 pi, then if I divide by positive n to the power 1 over 3, this is my Bn sequence and this is my An sequence, by the limit comparison test, sum of An also converges. Okay, so here I just use the limit comparison test because this inequality was obvious. We came up with that inequality because arcsecant of n for positive n is bounded by pi over 2, and I just took 2 pi, any number greater than pi over 2. You could write here pi over 2, you could write pi, you could write 3 pi over 2, whatever you want. Okay? Okay, so let us see now question number 9. Sum of nth root of n over n squared as n goes to starts with 1 to infinity. Nth root of n nth root of n, we talked when we did sequences approaches to 1. Okay? So how am I going to use this? Well, if this expression approaches to 1 as n goes to infinity, then if I take bn as a sequence to be 1 over n squared, this sum here, sum of 1 over n squared, is convergent what p-series, then by the limit comparison test, limit of an over bn is equal to the limit of nth root of n over n squared over 1 over n squared, which is equal to, well, this expression approaches to 1. We cancel these two. 1 over 1 is 1, which is greater than 0. So because the limit of an over bn is greater than 0, both series, sum of bn and sum of an, behave the same, because that means that either both of them are convergent or divergent. Since sum of bn is convergent, that implies that sum of an, nth root of n over n squared, is convergent. Okay, we have 4 more problems. So problem 10, sum of ln of n to the power of 3 over n to the power of 4. Okay, so here I can compare it, take sum of bn to be 1 over n to the power of 4, which is a convergent p-series with p greater than 1. Okay, but then the limit of an over bn is equal to the limit of ln of n to the power of 3 over n to the power of 4 over 1 over n to the power of 4, where these two cancel, and I get the limit of ln of n to the power of 3. And this limit, as n goes to infinity, is equal to infinity. And now be careful. The limit comparison test works in such a way that if the limit of an over bn is infinity, then I need the sum of bn to be divergent. Look at the nodes. Okay? And I have limit of sum of bn is convergent. So here my limit comparison test is inconclusive. I cannot work with this one. Okay? So what do I need? I need in a way to show that these I need to change this series somehow so that this limit is either going to be 0 or some constant, definitely not infinity. So as you can see, sometimes our choice of bn is not as we expected. It's not always take the highest exponent in the denominator. Okay, so what else we can do? So again, I'm doing 10 and I'm trying to figure out how this function behaves. So now I'm going to take sum of bn to be sum of 1 over n cubed, again convergent p-series. Okay, but now limit of an over bn is equal to the limit of ln of n cubed over n to the power of 4 over 1 over n cubed. That's equal to the limit of n cubed times ln of n to the power of 3 over n to the power of 4. And now, if you cancel this, you get the limit of ln of n cubed over n cubed, okay, which is equal to the limit of ln of n over n to the power of 3, and when n goes to infinity, this ratio we already talked when we talked about sequences goes to 0, or simply take the L'Hopital's rule if you're not comfortable with this. 0 to power 3 is 0. Now I have the limit comparison test says if the limit of an over bn is 0 and sum of bn is convergent, then sum of an is also convergent. Okay. Now something similar will happen with problem 11. Sum of square root of ln of n over n, as n starts with 1 to infinity. Okay, and now again this is going to be a tricky part here, and I will let you to prove it by yourself by giving you a hint here what to take for bn. Take 1 over cubed root of n squared. So you figure out what kind of series this is, and then find an answer for this one here, and on Monday I'll give you the answer, okay? So either use the comparison test or the limit comparison test with bn, which you should figure out whether it's convergent or divergent, and by using one of the tests, figure out what does that say about our problem right here. So problem 12, sum of 1 over n to the power 1.1 times ln of n to the power of 3. Okay, I will take bn to be sum of 1 over n to the power 1.1, which is convergent p series with p 1.1 greater than 1, right? 1.1 is definitely greater than 1. Okay, but now ln of n to the power of 3, here n cannot be 1. I cannot start with 1. I have to start with 2 because ln of 1 is 0 and I cannot divide by 0. You have 1 and 1.1 times ln of n to the power of 3, right? For n greater than 2, this is a positive term, right? So this constant, this expression, n to the power 1.1 times the positive term is definitely greater than n to the power 1.1. As a matter of fact, wait a second. No, it has to be greater than 1. So here I have to start with 3. My bad. Sorry about that. I have to start with 3. So when n starts with 3, ln of n is greater than 1. So ln of n to the power 3 is greater than 1. So this inequality holds. Well, then if I take the reciprocal, n to the power 1.1 times ln of n to the power of 3 is less than 1 over n to the power 1.1. This is my bn. This is my an. So by the comparison test, sum of an is convergent. Here the limit comparison test with this particular expression for bn would also work, because you would get that the limit is going to be 0. And finally, the last series for this video is the sum of 1 over square root of n times ln of n. And I want to remind you that the sum of 1 over n times ln of n to power p is the logarithmic p series that is convergent for p greater than 1, right? And for the other values, for the values less than 1 is divergent. So take as b, sum of bn, this series to be defined as 1 over n times square root of ln of n, which is 1 over n times ln of n to the power of 1/2, because this p is less than 1. We're talking about divergent logarithmic p series, because p is 1/2 less than 1. Okay, and then we can just use the comparison test here again. So an is square root of n square root of ln of n, and I'm comparing it with bn, which is n, well, sorry, this is the reciprocal. So if I compare square root of n square root of ln of n with n square root of ln of n, well, these two cancel, right? So I have that n is greater than square root of n, or if you take the reciprocal, square root of n times square root of ln of n is greater, if you take the reciprocal, the inequality flips, greater than n square root of ln of n. This is my bn, this is my an, and then if you look at the comparison test, this implies that sum of an, because this sequence is greater than the sequence bn, and the sum of bn is divergent, this implies that sum of an is divergent by the comparison test. Thank you very much.